gravitation plays a key role in mathematical physics, and in the previous lecture we considered one example that was related to stationary temperature field, and temperature field is a scalar field. So today I want to consider some examples related to vector field. And so the first example would be if we have a fluid flow somewhere in, say, R3, three-dimensional space, and we have some volume, omega, with the boundary, and we are talking about velocity vector, so we have vector field. At each point we have a vector. And assume that our fluid has a density which is constant, right? So density doesn't change, we have constant density. Another assumption would be that our velocity field V is conservative and there are no sinks and sources. So conservative, if we transfer it to the language of mathematics, it means gradient field, and it means that there is a potential function, potential phi, such that our vector field, our vector V is not just a vector, it's vector that is gradient of a certain function. And physicists likes to put here minus, so I put the minus here, but it will not affect our consideration at all. So we have a conservative vector field for velocity, so velocity is a gradient of some potential phi. And if we have such condition, that automatically means that our field is irrotational, because if we compute curl of V or rotor of V, then that would be determinant of ijk, then we have derivatives with respect to x, y, and z, and then components of our vector. But since our vector V is a gradient of function phi, so our function v1, v2, and v3 are with the sign minus derivatives, partial derivatives of our function phi. And then when we plug here ijk, when we plug, so here I put derivative with respect to x, y, and z, just I wrote, copied it in a lazy way, and here also derivatives of function phi, right, this vector, and then we can rewrite this and take into account that second partial derivatives are continuous, so derivatives with respect to, if we differentiate first with respect to z, then with respect to y, we will get the same function as derivative with respect to y first, then with respect to z, and then we will get 0. Right? So here I just wanted to show that if we have a gradient vector field, then automatically it will become irrotational. And also, since there are no sinks, sources, and constant density, we assume that our fluid flow is incompressible. And incompressible, or we can say it's solenoidal field. So divergent V equals 0. And here I just remind you the definitions of divergence, and also it will be convenient to review curl and gradient. So if we use the del operator, which is I d dx plus j d dy k, so here ijk our basis vector, unit vectors, so then when we have v equals negative gradient phi, so that would be del acting on our function phi, right? So our del operator, if we have a scalar function, it makes results in a vector, so we'll get vector. Then curl, it was a cross product of our del operator and vector v, which we had here. And finally, divergence is a scalar product of our del operator and vector v, and as a scalar product it will results in this sum, so it will be a scalar, right? Our curl was a vector, that's why we put here 0 vector. Okay, and then what we have if we combine these two, divergence v equals 0 and v is a gradient field, then if we want to rewrite everything in terms of function phi, we will get that with sign minus, that would be divergence of gradient phi, or we can write it sometimes in some literature people write it as nabla squared, or we can write it as delta, which means Laplacian, and we do everything of course in Cartesian coordinates here, so the Laplacian will be just sum of second derivatives, and from these two conditions we will see, since divergence v equals 0, so this would be equal to 0, and then we will see that our function phi is a harmonic function, or it is a solution to the Laplace equation. Let's discuss another example. Let's discuss Maxwell's equation and see how Laplace equation can be a simplification in a certain situation of Maxwell's equations in classical electromagnetism. So Maxwell's equations are a set of partial differential equations, and this is a set of coupled equations. So it involves Gauss law for magnetism, Maxwell's Faraday's equation, and Ampere's circulation law. So let me describe the notation. So E is electric field, and this is a vector field. So vector x here describes the spatial coordinates. T is time. So vector, so it's not actually a vector, and this is a pseudo vector. So this is magnetic field is defined by B, and rho is a scalar electric charge density, and J here is electric current density, and epsilon naught and mu naught are electric and magnetic constants. Right, so now let's look at the first equation, Gauss's law. It describes a relation between electric field and rho, which is charge density, between electric field and charges. This second equation, Gauss' law for magnetism, tells us that B is divergence free, or that field is solenoidal. Maxwell-Faraday equation tells us that time varying of magnetic field induces electric field, and this elastic equation, Ampere's circulation law, tells us that magnetic field is induced by current density and change in electric field. And then we can consider quasi-static approximation. So if we assume that magnetic field changes with time very slowly, then instead of this equation we can write just the curl of E equals 0 approximately, and then we have this first equation, Gauss's law, and then we can write these two equations, then they are decoupled from the rest of the equations, and we have this simplification. So now let's look at this simplified model, and in the previous lecture in the previous example, we just seen that if we have a gradient field, then this field is irrotational. So now we have an irrotational field, curl equals 0, and the question is whether or not this field is gradient. So do we have the converse statement? So to answer the question, we claim that if we have an irrotational field, then exists such a function phi that is called potential function, such that E is gradient of P. So we want to show that irrotational field implies that the field is actually a gradient field. If you want, you can put here a minus, but it will not change the computation. It's only in the end we can see where it will be different. So now let's look at this equation, and then let's integrate it over a surface. Assume that we have somewhere in our space a contractible piece of surface, so surface without one piece, no holes. And if we integrate the right hand side of this equation, we still get 0, but in the left we will have this integral. So consider this integral, we can think of that as a flux of the curl of the surface, or its normal component of our curl. And then we can use Stokes' theorem, where we have that integral over the surface equals integral along the boundary, and along the boundary we will be integrating the tangential component of our vector field. And we can rewrite Stokes' formula in just differential form notations. So then we will have d omega is integral over s equals integral of omega along the boundary, and it's still 0 since we have it here. And what is omega now? Omega in our situation is if we give the following notations: if first component of vector E is Ex, second Ey, and third E sub z, right? If this is our vector E, then omega is this differential form, Ex dx plus Ey dy plus Ez dz. And so, by the way, if you want to review the Stokes formula, please find lecture B in the description to this lecture. And then we will compute exterior derivative. If you forgot this stuff, it's also see the description, it's lecture A. Then d omega will be this 2 form. And so what do we have? We have this Stokes formula written here, and integral over any contractible surface is 0. So if we change surface, and we always get 0, so it means that d omega is 0. If d omega is 0, then it means that omega is a closed form. And now, since S is contractible, then by Poincaré lemma, omega is exact. And that means that we can find such a function. Since omega is one form, we can find such a function that omega is just d phi, differential of phi. And so, in other words, we can say that electric field is the gradient field. So again, if you want to have here minus, you can replace this this version of phi with another version of phi with a sign minus. And now let's go back to our electric quasi-static approximation. We had these two equations that curl E is 0 and divergence equals to rho over this electric constant. Then from the first equation we just got that our electric field is a gradient field, and then if we plug this into the second equation, if instead of E we will plug gradient phi, then we will get that Laplacian phi equals rho over the constant. And that is Poisson's equation, so the difference would be depending on whether we choose which phi we will choose here. We might get a minus here, but then if there are no charges, if rho is 0, then our phi of any kind will be 0, so we have for phi Laplace's equation. Let's consider an example related to gravitational field. So a gravitational field is given by this formula where we have x would be our vector of our coordinates, small g is the universal gravitational constant, and m is the total mass that generates this field. And so here I rewrote this vector in component-wise form, right? So that first component would be x1 over this expression, x1 squared plus x2 squared plus x3 squared to the 3 halves, and the rest of the components. And the claim is that exists such a function phi, which is called gravitational potential, such that we can rewrite our gravitational field using our function phi. And again, this comment about sign. So I will choose a positive sign. So, and here it's just instead of a proof, I will just give you present you this function phi, which we can check, and this is this function, and we can easily check that if we compute gradient of this function, all partial derivatives, we will get our vector g, right? Indeed, so what we have here, just suppose this is just a constant, we can pull this out, and then we have phi is this expression to the power -1, so derivative would be -1/2, the whole thing to the -3/2, so here is negative, here is 3/2, and times derivative of inside. If we differentiate with respect to x1, for instance, it will be 2x1 and 2 from here when we have -1/2. 2 and 2 will be cancelled, we'll get this first component, and similarly we can get the other two components. Right, so phi is indeed a potential. And then the next claim would be that our function phi, our gravitational potential, satisfies Laplace's equation if we avoid the origin, if magnitude of vector x is not 0, right? So outside of the origin. So, and to compute Laplacian, we will write it as divergence of the gradient, because gradient is already here. We just need to compute divergence. So we need to differentiate each component with the corresponding x and add them all together. So here I wrote it as a sum from 1 to 3, right? So for instance, if we differentiate this, the first component with respect to x1, and I also introduced here notations just to simplify the computations, right? So instead of when we will be differentiating, we will use this fraction rule, right? So the bottom must be squared. So I put here 6 because I rewrote it in terms of the magnitude, right? And so this expression would be just squared to power 3, and then we just honestly use quotient rules. Maybe I should skip the comments. The computations are written here, and then so it will be derivative of x1, then bottom is just multiplied minus the top times derivative of the bottom, and then we will have this expression, right, for every xi, and then we just sum them all together, and we will see. So here in the middle I just divided everything by magnitude of x because I have this assumption, and then we will get in the end that indeed we are getting 0, so our gravitational potential phi satisfies Laplace equation outside of the origin. Thank you.